In today's video we're going to look at angles, and we're going to look at these in both degrees and radians, which may be a new concept that you haven't seen before, and we're going to relate the two and look at things like circumference and area of circles, etc. First thing, what is an angle? An angle is just a thing that is made by joining two rays at their end points, and we tend to assume that angles are in standard position. That means that our initial ray will be along our x-axis here, and then the other ray will be somewhere else, let's say over here, and then we say that if we sweep out angle like that between the two rays, that would be our angle between them. Okay. We can sweep out that angle in either the counterclockwise or the clockwise direction. If we sweep the angle out in the counterclockwise direction, like I have here, so I started at that positive x-axis and my second ray was somewhere counterclockwise to it, then that tells me that the angle is positive. Okay. If I start at that positive x-axis and I sweep the angle out in the clockwise direction, then this angle is negative. Okay. I think we've all seen angles in terms of degrees before. Okay, we know that there are 360 degrees in a circle. So if I start out with my xy axes and I draw out that original ray, and then if I go all the way around in a circle here, I've gone round what is known as 360 degrees. It's a measurement. Okay, it just tells me how big that angle is. So if my first ray is on that positive x-axis, and then I sweep out an angle such that my second ray is also on that positive x-axis, so I've got all the way around in a circle, I've gone around 360 degrees. If I only go halfway around so that that second ray is on the negative x-axis, then I've gone round 180 degrees. And you can break it up even further. If I only went a quarter of the way around, I've got 90 degrees, etc. Like I said, instead of just measuring angles in degrees, we can also use this other measurement, and that's called radians. What is a radian? I will define it here and then we will draw it out and relate it to degrees. 1 radian is just the angle that we get when the radius r is equal to the arc length. We'll call that arc length S. So if I were to take, again I can draw this on the xy axis, if I were to take this ray here, and whatever its length is, I call it R, and then I sweep out an angle such that that arc that is created that joins the end points of these two rays here, so both the rays are going to have this length R. If this arc length S is equal to whatever the radius is, so whatever the ray length is, then the angle that is inside is known as 1 radian, or 1 rad. Okay. So it's just the angle that is formed when we take the radius. You can also draw this as a whole circle if you wanted to dot it out as a whole circle, since we're talking about a radius, where the radius of that circle equals the arc length that we sweep out, then that tells me that the angle in the middle of the two rays is going to equal 1 radian. How does this relate to degrees? How can we relate degrees and radians? The answer to that is that 180 degrees is equal to pi radians. Okay, we'll talk about why, but I'll quickly draw this out. So if you go round, you start again on this positive x-axis, you sweep out an angle here, so you have 180 degrees. That is also equal to pi radians. Why is this? If I were to draw out a whole circle here, okay, a whole circle is 360 degrees, is that internal angle. Okay, let's think of this in terms of radians for a minute. Okay, I'll draw this again. I'll just draw out a circle and I will draw out its radius here. Okay, the circumference of a circle is 2 pi times the radius. Okay, that means that is the length of the arc, where let's say I start here and I go all the way around the circle. Okay, so it's just one massive arc where I've gone the whole way around. Okay, we said that 1 radian was where the arc length equaled what that radius was. But this time I've gone 2 pi times the radius. So when I just went 1 times the radius, that internal angle was 1 radian. So when I went just whatever the length of the radius was around my circle, then I had 1 radian. But this time I've gone 2 pi times the radius all the way around my circle. That's the length of that arc, is 2 pi times the radius. That means that the angle that is swept out in the middle must be 2 pi times whatever the angle was when I just swept out 1 radius. Okay, so that must mean that the internal angle when I go the whole way around is 2 pi. Okay, because I had just 1 radian when I had an arc length of r, but when I have an arc length of 2 pi times r, that internal angle must be 2 pi multiplied by whatever the angle was when I just swept out by 1 times r, so that internal angle must now be 2 times pi. So that tells me that if I went the whole way around the circle, I get 2 pi radians. And we know that inside a circle I have 360 degrees. So all we have done here is divide both sides by 2 to tell me that 180 degrees must equal pi radians. So how does that help us convert between degrees and radians? Well, if we know that 180 degrees equals pi radians, okay, I'm going to give you both ways of how to do this. If we have x degrees, we're going to multiply x by pi over 180 to get the number of radians. Okay, that's just by rearranging what we have at the top. If I've got x degrees, then I'm going to multiply that number by pi over 180, and that's going to get me into radians, and that's all because of what we have at the top here. If I have x radians, we're going to do the opposite. We're going to multiply x by 180 over pi to get the number of degrees. Okay. That follows really simply from what we have at the top. Okay, 1 degree must be 1/180th of what I have here. Okay, so if to get 1 degree, I divide both sides by 180, which gives me pi over 180 radians. So 1 degree is pi over 180 radians. So then if I increase the number of degrees, I'm just going to multiply whatever I have by pi over 180 to get me the number of radians. Same thing when we try and convert between radians and degrees. If I have x radians, well, I know that 1 radian must be 180 over pi degrees. So if I multiply however many radians I have by 180 over pi, that will get me the number in degrees. Okay. Let's do a couple quick examples here. So my first example, I'm going to convert 30 degrees to radians. So like we said, we're going to take the number of degrees and we're going to multiply it by pi over 180. So if you simplify that, that would be 30 pi over 180, which would just be pi over 6 radians. Okay, so you can just cancel out the fraction. How about a negative angle where we've gone clockwise? So we're going to convert negative 45 degrees to radians. So again, I'm going to multiply by pi over 180 to give me negative 45 pi over 180. And if we cancel out that fraction and simplify it, I'm going to get negative pi over 4 radians. Then we can actually convert the other way. So we can convert from radians to degrees, like I said. So let's convert pi over 3 radians to degrees. Okay. Well, all we have to do here, like I said, is we are going to multiply that radians amount by 180 over pi. You should find in a lot of cases here, if you're dealing with standard angles that we're used to, that the pi should cancel out. You'll end up with 180 over 3, which is just 60 degrees. And we'll do a negative angle as well. So we're going to convert negative 3 pi over 2 radians to degrees. So we've got negative 3 pi over 2 multiplied by 180 over pi. Pi's cancel out. That will leave us, if you then divide by 2 multiplied by the negative 3, you're left with negative 270. So hopefully that's pretty simple. You just have to work with fractions here. A term that I want you to be aware of is something called a coterminal angle. Okay? Two angles are said to be coterminal if they have the same initial and terminal side. So if those two rays that we have when we sweep out that angle match up. You can go around in a circle as many times as you like, both clockwise and counterclockwise. But if you have the same initial and terminal side, then those angles are said to be coterminal. Okay, what does this look like? Let's quickly draw out our XY axes again. I've got my initial side here, my initial ray, And let's say that my terminal ray was here. So I know that I've got this angle, we'll call it alpha, that is swept out between the two rays. An angle that is coterminal to this is also the angle where I've gone all the way around and back up again. We'll call that angle beta. Alpha and beta are in this case coterminal because they have the same initial and terminal side. I also have the angle where I start at this initial side, but I go clockwise. Okay, and we'll call that angle gamma. Okay, so alpha, beta, and gamma all have the same initial and terminal side. We've swept two of them out in the positive direction, one out in the negative direction. But all of those angles are coterminal to one another. Let's do a quick example of this. Okay. Let's say that we're asked to list 3 angles coterminal to 70 degrees. Okay. If they have the same initial and terminal side, they must be multiples of 360 added on or taken away from that initial angle that we have. So let's say alpha was 70 degrees, which is the angle that we're looking at. To get that angle beta, I'm just going to add 360 degrees because I've got my initial 70 degrees, but then I've gone completely around in a circle again, another 360 degrees to land back at that terminal side. So one angle would be to take that 70 degrees and add on 360 to it. And that would give you 430. I could get another one by going another 360 degrees around. So I can then do 70 plus 2 times 360 degrees. That would give me 790 degrees. So that's another angle that's coterminal. And you could keep adding multiples of 360 to it. If we go back to this, I can also go backwards. Okay? I can take whatever my angle alpha is and I could subtract 360 degrees from it. That will give me that angle gamma that we have here. So if I take my initial angle alpha and I subtract multiples of 360 from it, I'm going to end up with some more angles that are coterminal to it. So we'll do one more by subtracting 360 degrees from it. So like I said, you can go in both directions here. Just add and subtract multiples of 360 from your initial angle and you'll get angles that are coterminal to the original angle. Let's do one in radians. So this time we're going to list 3 angles coterminal to pi over 3. Okay. So I start with pi over 3. And this time, remember we said that 360 degrees was the same as 2 pi radians. So I can add and subtract multiples of 2 pi to my angle in radians, and that will give me other angles. Remember, if you're in degrees, add and subtract multiples of 360 so that you're still in degrees. If you're in radians, we're going to add and subtract multiples of 2 pi, and that will give you coterminal angles in radians. So if I add 2 pi to this, that would give me pi over 3 plus 6 pi over 3, which would be 7 pi over 3. I can add another multiple of 2 pi to this. That would be adding 4 pi to it, which would be the same as 12 pi over 3 added to it, which is 13 pi over 3. And I can also subtract multiples of 2 pi from my initial angle. If I did that, I would end up with negative 5 pi over 3. A formula that is really useful to use is something called the arc length formula. Okay. it goes back to when we were looking at that circle with radians. Okay. We had our radius of the circle R, we have an angle in the middle here, and then we have the arc length S, which is the arc that's swept out between your initial and terminal rays. Okay. So that arc S is just part of the circle. The angle is the angle that is enclosed, it's called the central angle. And then the sector is the part enclosed by the central angle and the arc. So the sector is just that whole area there. When you have this arc length formula, it tells us that that arc length S is equal to R multiplied by theta. Okay, theta is that central angle that we have where we've got the initial and terminal rays. But a big thing here is that theta must be in radians, otherwise this formula doesn't work. You can kind of see that from our definition of radians. 1 radian, so when theta equaled 1, then that told us that that arc length equaled the radius, which was the definition of 1 radian. So theta must be in radians. If you are ever given theta in degrees and asked to find the arc length, make sure you do that adjustment first to get that angle into radians from degrees, and then you can go ahead and find that arc length. Okay. We're going to do a couple examples using this, and we're going to do this a few ways around, using this in a couple different ways to find S or R or theta. Okay. The first example I'm going to do is to say that an arc length of 10 centimeters subtends an angle of 50 degrees. What is the radius? Okay. If we were to draw this out, I draw my circle out like this. Okay, I've got my radius R that I don't yet know. My arc length is 10 centimeters, and I'm told that theta is equal to 50 degrees. Problem is that I've got this angle in degrees. I need to put it into radians, which means that I've got to multiply it by pi over 180, which would be 5 pi over 18 radians. Okay. Now I can use my arc length formula. So I know from my arc length formula that the arc length is equal to the radius times the angle. Well, I need to find the radius, so I'm going to divide both sides by that angle. So that tells me that I would have 10 divided by 5 pi over 18, which would be 180 over 5 pi, which is approximately equal to 11.46 centimeters. Okay. Whenever you're dealing with sides, I would recommend you put them to 2 decimal places. When you are dealing with angles, try and keep them as fractions if possible, especially when you are dealing with radians. The next example that I'm going to look at, again, is going to be where we use this formula to find the radius. So I've got that an arc of length 15 centimeters subtends an angle of 70 degrees. So let's draw this on a circle. I've got a 70-degree angle, and I know that the arc length is 15 centimeters. The question is, what is the radius of this circle? Okay, we're going to use our arc length formula again, and remember that we have to rearrange it And then we have to put that angle theta in terms of radians. Right now it's in terms of degrees, but it has to be in radians. So the first thing we have to do is multiply this by pi over 180. And when you cancel that down, it gets to 7 pi over 18 radians. So now that tells us that our radius is equal to 15 centimetres divided by 7 pi over 18. And when you plug that into your calculator, you get approximately 12.28 centimetres. We can also use this in a different way by trying to find what that central angle is. So we're going to use the same formula again, but this time in this example, we're going to be looking for that central angle. So this time I'm going to have an arc of length 5 pi over 2 centimetres. This will help us in order to find that particular angle. It will make it a nicer number. That's why we've got an arc of length 5 pi over 2. So the arc of length 5 pi over 2 centimetres subtends a central angle theta in a circle of radius 6. And we've got to find that central angle, but we're going to find that central angle in degrees. Now, if I draw this out, we're told that the radius of the circle is 6 centimetres. And the angle that this arc subtends is what we're trying to find in degrees. And we know that our arc length here is 5 pi over 2. Now, when we find theta, originally we know using that formula it's going to be given to us in terms of radians. So we will have to do a conversion at the end. So if I rearrange this, I get that theta is equal to S divided by R. S is 5 pi over 2 divided by 6, which is 5 pi over 12 radians. I now need to find that angle in terms of degrees, which means I've got to multiply it by 180 over pi, which when you cancel it down, you get 900 over 12, which is 75. So in this particular problem, I was just going to ask you to find that angle theta in terms of degrees. So make sure that you do that extra step. You find what the angle is in terms of radians using that formula, and then you go ahead and do that conversion to put it into degrees. The next thing that we're going to do is to find the area of one of these sectors. So remember, when we have this circle, we've been looking at arc length. Okay, we've had this radius r, we've had this angle that this particular arc length s subtends, and that was theta. What I now want to do is to find the area of this particular sector of the circle. And the way that we do this, it doesn't actually involve the arc length. The area is actually equal to 1/2 r squared times theta. Again, theta is in radians. Okay. Let's look at some examples of this. So now I'm going to find the area of a sector of a circle with a radius 4 inches where the angle inside that sector is 50 degrees. Okay, how do we do this? Well, again, let's go back to our formula. I need the radius and I need that angle, but that angle has to be in radians. So the first thing I have to do is to convert degrees to radians. So I multiply it by pi over 180, which gives me 5 pi over 18. Now I can plug everything in. So the area is 1/2 multiplied by 4 squared multiplied by 5 pi over 18. 4 squared is 16, divided by 2 is 8. So that would give me 40 pi over 18, which when we cancel it down is 20 pi over 9, which is approximately 6.98. And this time we're looking at an area. Now my radius was in inches, so this is going to be inches squared. Our particular measurement here is going to be square inches. So remember that with area, it's always going to be the square of whatever unit of measurement you used for your radius. In this next example, I'm going to find the central angle. So I'm going to be given the area and I'm going to be given the radius, and I've got to find the central angle. So this time, the area of a sector of a circle with radius 6 centimeters is 34 centimeters squared. And we want to find that central angle. And again, we're going to try and find this in degrees. So when we initially use that formula, it's going to be in radians, and then we'll do the conversion at the end. So find the central angle in degrees. Okay. So again, going back to our formula. This time we have to do some manipulation. Okay. We want to find theta. First thing I'm going to do is multiply both sides by 2. And then I've got to divide through by r squared. So that gives me theta is equal to 2a over r squared. Okay. So if I plug in what a was 34. So 2 times 34 gives me 68. And my radius is 6. So multiply that by itself will give me 36. And then if I do that, I end up with approximately 1.89. Okay, now that is my theta in radians. It's 1.89 radians. There is no pi in here. Okay, it is just in radians. We get this constant value back. A lot of times radians does have pi in it, sometimes it doesn't. Remember, 1 radian is just the angle that we get when the radius is equal to the arc length. So this time we have 1.89 radians, okay? But we want this in terms of degrees. So I'm going to multiply what I got in radians by 180 over pi, and you get approximately 108.29 degrees. What I tend to say is, and it completely depends on the problem, etc. But in general, if you give me measurements in terms of length to 2 decimal places, for angles, as long as you give it to me to at least 1 decimal place, I'm happy. But in this case, I went to 2 just to make sure. But as long as you give me angles to at least 1 decimal place, I'm happy. And in our last example, I'm going to find the radius of the circle. So again, this time I'm going to be given the angle and the area, and we're going to find the radius. So given a sector of a circle with central angle of 40 degrees, has area 80 centimeters squared, find the radius. Okay, let's go back to our formula. A is equal to 1/2 r squared theta. This time I am looking for r. I'm going to multiply both sides by 2. Then I'm going to divide by theta. And now I have to square root. I'm only going to take the positive square root here because we cannot have a negative length for the radius of a circle. So I'm just looking at the positive square root here. Now, we've been given theta in terms of degrees. Remember, we have to put it in terms of radians. So the first thing I have to do is to multiply it by pi over 180, which would give me 2 pi over 9. Now I can use this theta of 2 pi over 9 in my formula. So r is equal to the square root of 2 times 80, which is 160, over 2 pi over 9, which is approximately 15.14 centimetres.